Welcome. If you just joined us online, you can ask questions by turning off the mute. We already took roll in here. Is there any questions in particular you want to look at today in preparation for the exam next time? Again, don't show up at the classroom next time. The exam is all online. I'll send you an email at 8 o'clock in the morning. You have till 9:15 to finish it and send it back. The easiest thing is to print it off and then write your exam and then either photograph or scan it and send it back to me. But if you don't have a printer, you can look at it on your phone or your iPad or whatever you've got handy to look on. So just learn how to take your emails off before Thursday and put them in some way you can look at them. And if you need to, write on blank pieces of paper, put your name at the top, photograph and send it on your cell phone, or photograph it or scan it is better. If you have a scanner or a printer that scans it, and send it back. Either way works just fine, as long as I get a copy of the exam. This is the first exam, so I expect a few technical problems. If you can't send it. I know some people are having internet trouble. Send me an email and I'll be considerate. We have the practice problem for the people online already, so hopefully they've got it down. But if you didn't get the practice problem in my email, then that means you probably won't get the exam in my next email. So that was sort of a test to see if you're going to get the exam. All right, that all being said, then anything in particular that you'd like to look at, this is the practice exam online. One of them was missing. I know the answer number 15 was missing. We can do that one today if you need to. And then I wanted to make one comment also. The very last problem, to sketch these things, we didn't get to that yet, so we're going to delete that one. So the first thing today is to delete number 23 from the practice problems. Now, the practice problems are not comprehensive. I might ask questions that are not on there. Not a lot. If you can do all problems similar to these, you'll pass the thing. But if you want an A, you might have to do all the homework problems. All the problems will be similar to homework. But there might be some that aren't similar to the practice test. Nonetheless, the practice test is exactly the way I write exams. Don't let it scare you. It's probably at least twice as long as a real exam. I'm not going to ask anything so many questions at all. I'll make it so you can finish it in less than an hour and a quarter and have time to still film it and send it back. So it's probably an hour exam is the idea. And it's open book. Open notes, you can use your computer. These computers, some of them can do trigonometry. So what I'm going to do on there is not just what it says on here. I'm going to ask you to write out your intermediate steps and sometimes more than that, draw a picture, something that the online calculators can't do. So exam Thursday will require work. So make sure you can put some work, like sketch the unit circle, in order to calculate your values. Sketches they won't do online. But there'll be these kind of problems. So it's online. Don't show up to UCO unless you want to sit at a computer at UCO to do it or something. I won't be at the classroom. I'll write it out then. Exam comes by email. If for some reason you're still having a problem with your registration, let me know because it won't be on my email list, right? All right. Any other comments on the exam before we do practice things? All right. Have you looked at it? Is there anything in particular you want to look out for there first? I might charge ahead a little bit at the end so we don't just do review and exam this week, but actually do a little new material. But and I say off the practice exam, also off the homework too, because remember some of the problems will be from homework that aren't necessarily on the exam. Most of them will be from some of the practice exam problems. easy, huh? Everybody did it and thought it was trivial.
Professor, could we go over number 8?
Okay, yeah. All right, so here's a good example then. Number 8 off the practice set. If you know that the sine of theta is minus square root 2 over 2. This is a good one. And theta is in, I'll abbreviate here, quadrant 4. Find cotangent theta. Why is this a good problem? It's a good problem because the online calculator won't do it, right? It will do some of it, and you can figure out how to make the online calculator do some parts, but if you know nothing, you won't be able to do anything. So what you do here is you can draw a picture. And here's the unit circle. Now, sine theta equals minus square root 2 over 2. What does that tell me about the point on the unit circle? Sine theta is the y-coordinate, right? Well, I want the y-coordinate equal minus square root 2 over 2. Well, minus square root 2 over 2 is about minus 0.7. So if I want to draw it, I'll draw it down here. It doesn't have to be real close. But here's y equals minus square root 2 over 2. From algebra, that's a horizontal line, right? Now, that has 2 points of intersection with the unit circle. So there's 2 possible angles it could be. It could be this angle, or it could be this angle. But one of those 2 angles makes the sine equal minus square root 2 over 2. All right, those are the only ones whose y that touch the unit circle at y equals minus square root 2 over 2, those intersection points. So what do? I say, oh, it's in quadrant 4, so it's not that one. It must be this one, right? And then I'll drop a perpendicular to the x-axis rather than the y-axis to be conventional. And then I know that this side of the reference triangle, we call it, since I went down to minus square root 2 over 2, must have length plus square root 2 over 2. And this side is length 1 since it's a unit circle. And now I recognize if 2 sides of a right triangle are known, the third one is automatically determined by the Pythagorean theorem. I don't have to figure it out because I've already memorized it. Square root 2 over 2, 1. The last side must be square root 2 over 2 by memorization. Or you can figure it out if you want. But that's the triangle. Now I want to know for that angle theta, this implies, that's what this means. If this is true, then this is true or implies that the cotangent of theta, how's that defined? It's cosine over sine if you want, or just x over y. Either way, cosine over sine or sine or x over y. The x coordinate is square root 2 over 2. The y coordinate is, I have to go by coordinates now, not these lengths. The x coordinate, since I went right, is plus square root 2 over 2. The y coordinate, since I went down or was given it, is minus square root 2 over 2. Evidently, the cotangent is negative 1. That's exactly the kind of problem I'd like to ask you on the test. Something like that. That would make sense? And you can figure the angle too. And then another way to do this, if you know the inverse trig functions, which we're going to do shortly, you can say theta is the inverse sine of this angle, figure out what the angle is, and then take the cotangent of it. But on the calculator, it's not there. You'd have to take 1 over the tangent. So that's all more complicated. And I might ask you to draw the unit circle in any case. So be able to do it on the unit circle at least. What would you like to see next? I'm finding an eraser here. Please, again, 30. All the others are. What do you?
We do 21.
Yeah. I asked you, even though I have a few in mind, because I think you have a better idea what's hard than I do. Once I do enough of these, I don't remember what's hard about it. Said 21, right? Yeah. Let's see. Oh, let's do it on there. Oops,
It was already on that.
yeah, there it goes. Sorry. All right, this is a hard one, I gotta admit. What might happen on the test, what I've done before, is I've said, what's your rotational speed on Mars or Mercury or something like that, some other planet, if you're standing on the equator. So listen, I could ask questions just similar and change the numbers around that way. So here's 21. It says the Earth rotates in 23 hours, 56 minutes, 4 seconds. Now, last time we did it with 24 hours. This is the actual rotation time to do one complete rotation. We said it has to do a little bit more than one rotation to complete a day because it's also moving around in its orbit as it's turning. So it turns a little more than one time around to complete a day. That's why a day is 24 hours. 23 hours, 56 minutes, and 4 seconds. And has a diameter of 7,126 miles. Now, if you remember the problem on the UCO practice sheet, I gave you something else. I think I gave you the radius in 24 hours. So I've changed it a little bit here, right? I changed the time to the real time, and I gave you the diameter rather than the radius. So that way you can't just memorize the answer, right? If you're standing on the equator, how fast are you traveling? Ignoring that the whole galaxy is moving itself and then the sun is moving within the galaxy and all that sort of stuff. Einstein said it's all relative, right? How fast are you traveling? With respect to the sun, is what he said, or with respect to the center of the Earth. Standing on the equator. As I said before, how fast would the wind be blowing if the Earth, if it didn't move with the Earth? It didn't turn with the Earth. So on this one, you can say, I'm asking for the linear velocity, v, that I'm traveling. I really think on all these applied problems, it's best to draw a picture. Here's the picture. I can draw a sphere by drawing a circle and then an equator like that, dotted back to make it look sort of translucent. Here's me standing on the equator. I want to know how fast am I moving? This goes into the board here. Well, I can say that I have this equation from dividing the s equals r theta equation by t, that the linear velocity that I have is the radius of the Earth times the angular velocity, omega. Now, the radius of the Earth is not the diameter, it's the diameter divided by 2, right? The diameter is the distance clear across. The radius is 7,926. Miles. Doesn't hurt on these problems with the rates also to write the units. You don't have to in general, but sometimes I'll ask you for units and sometimes not. In this case, I did, right? I think did I say miles per hour? Yeah, miles per hour. The nearest mile per hour. Let's put MPH, which means the same thing. How many miles times the omega? What's omega? Well, it turns one rotation. How do I write this? I can write this in 23 hours plus 56 minutes is 56/60ths of an hour. I'm teaching this in algebra at the same time here, making sure you're expert on this stuff. Plus 4 seconds. How many seconds in an hour? Not 60 in a minute, but yeah, 60 times 60 or 3,600. Right? So 4 3,600ths of an hour is 4 seconds. 56/60ths of an hour is 56 minutes. And so these are all hours, right? I could just scratch these off and say the whole thing is hours. One rotation every 23 point something hours. And that's not going to give me my whole answer. Why not? My answer is now miles rotations per hour, and rotations has units. So how do I get rid of rotations? Aren't you glad you came to class today? These are hard ones. Oh, this is a hard one. Most of them aren't this hard. You can say, well, there's 2 pi radians in one rotation, right? And now the rotations cancel. Oops. Like this chalk, you can see it online, right? In fact, let me move this camera here so I'm thinking, because I know it's tracking with me right now, and I need, sometimes people can't follow when it does that. It's always a delay doing this. You can see the whole problem would be good, right? There we go. Okay.
Professor Stapleton, it's following you again.
It is. Oh, okay. Jeez. Yeah, thank you very much. I appreciate that. I'll get used to it. I forgot to push one of the buttons. There we go. Thank you. All right, so there it is. And now radians is unitless, so I can cross that off or put it on anytime I want. And now I've got miles per hour. There it is. Well, I just need to take 7,926 times 2 pi. Oh, wait a minute. There's 2's that cancel. I cancel that 2 with that 2. I could call it 7926 pi over 23 plus 56/60ths plus 4 3600ths. And then times 1 doesn't do anything. There it is. I just have to make that calculation. And then be careful, make sure you put these parentheses on here in your calculator. This is a calculator challenge too. If you don't put these on, what is it going to do? It does order of precedence of operations, where it does first parentheses are the strongest, then it does products and quotients at an equal level at the next stage, and then it does additions and subtractions at the next stage. Oh, I forgot powers in here. Parentheses, then powers, like a hat, caret on your calculator. Parentheses, powers, products and quotients, sums and differences. In that order of precedence, unless you force it with parentheses, it'll do these things. So we'll do the division here by 23, and then it will add these things afterwards, unless you put your parentheses on. So this is a way to be frustrated all night, is to keep trying this over and over without parentheses. And then also pi, because we're on this problem, going to need a lot of digits. I'm not going to put 3.14. I won't get enough accuracy. I'm going to put, I could try 3.14 or 159. That might work if I memorize that. Easier to use the second pi key. So let's try that. 7926 times, I wish I could put this in the overhead, but I'm having problems with that. Pi, second pi on the calculator. And all divided by parentheses. All that stuff. There's so many keys. You should at the end take a look at it and see if it looks like you typed the right thing. This is where the graphing calculators are really nice. On their display, they'll show you the whole thing you typed and you can look at it. Whereas a $10 calculator does the work perfectly, but if you make one keystroke wrong, right, you don't know it. And I get 1,040.35, blah, blah, blah. These digits out here probably aren't good because I already rounded this off to the nearest second. But in any case, I said round it to the nearest mile per hour in instructions. So I'll say, you don't have to write squiggly equals. It's about 1,040 miles per hour. And I'll rewrite the units this way. You can write the units either way you want. We'll be able to do one like that. That's a good problem too. Probably all the hard ones will be on the test, right? Depends on what mood I'm in. So, be nice to me today. All right. No, I'm in a good mood because I came back from vacation. What else would you like to do? I pick one that somebody else was asking me on email, because I think this is a tough problem. We didn't actually do it in class, even though it was in homework. I want to make sure you can do it on the test. It's like one we did in class. Not quite. It's two parts, each of which is like what we did in class. This would be, it's on both the homework and the page. Oh, it's right there. Ready? That's number 20. Find the area of the windshield that's wiped by a blade that's 15 inches long, and I don't have this on. You can look at it on your practice test if you printed it off. Find the area of the windshield cleared by a wiper blade 15 inches long and 4 inches out along a 19 inches wiper. So it's like this. I drew a picture because wording is always clumsy. It's got a 15-inch blade, that's the rubber part, 4 inches out to the blade, and it swings back and forth like this. How much is this blue area that it clears? And on a curved windshield, this isn't exact. Maybe it's cheap or something. I'm a flat windshield, and it's pretty accurate. All right, how much is this area? If it's a 105-degree turn, 15-inch blade at the end of the 4-inch, it's not cleared. Here's number 20. I won't redraw the picture since it's up there. Move the camera back though. Uh-oh. Moving mysteriously. I must have touched something. Sheesh. Mouse is life of its own. Right. There it is. Let's do it over here. Maybe it's worth drawing a little bit of it. 105 degrees, 4 inches, 15 inches. I guess since we can't see it online. What is this area A? Well, what you can do is you can say that area A is the area, oops, I'll be able to draw really. The area of the big sector here of radius 19 inches, this whole thing, take away this little thing here that's not cleared. So 19 inches minus, oops, the little one here, that's 4 inches. It's a little more than 90 degrees, 4 inches. And this is 105 degrees on all three of it, on all three of these. But this is a sector, right? A slice of pizza. So this is 1/2 r squared theta. I'll call it r1 squared because it's got one radius. And then take away 1/2 r2 squared theta, or r2 is the other radius. So that's where it's a trick. It's got two parts, right? It's a sector minus a sector. This applies to all those things you see out in the fields and farms, right? They've got these kind of contraptions that water the field. How much of the field is watered, right? I always wanted to know. You can figure it out. All right. So this is 1/2 times R1 is 19 squared, and theta is 105 degrees, and immediately I don't have it right. What's missing? Yeah, the formula only works in radians, right? You're going to lose a couple points in the test if you don't convert it to radians, because you get probably 100 miles instead of, 4 square feet or something like that. If you get an intractable number, that's probably you forgot to convert it. Times 2 pi radians for every 180 degrees. You can also tell if you just write in your units like I suggested, because you'll get, if I put in the units here, 19 feet. You'll get feet squared from here times degrees. You won't get square feet. You'll get square feet times degrees, and you'll know you have the wrong amount here. And then minus 1/2 4 squared. Oops, 4 feet, 4 squared, 4 feet squared times theta is again 105 degrees times 2 pi radians for every 180 degrees, Once again, the degrees cancel. And I've got square feet radians, but radians goes away anytime, right? So I've got square feet on both of those. That's a good sign. Now, here's something you don't have to do that I like to do. You can compute this directly in your calculator and you'll probably get the right answer. I make so many calculations, I often get a mistake. I notice there's a lot in common in these two terms. What are terms? Things that are added together, right? Factors are things that multiply together. Terms are added together. In this case, I'm adding a negative. So I'll call them terms. This is a term and this is a term. I'm reminding you of some of these things. These terms have a 1/2, 105, 2 pi over 180 in both of them. It's only the 19 squared and the 4 squared that's different. So I might write this as the common factor, 1/2, 105 degrees. I can get rid of the degrees, already canceled them, right? 1/2, 105 times 2 pi over 180. That's in both of those. And then multiply that times 19 squared. 19 squared times this gives me this term. Minus 4 squared. 4 squared times this gives me this term, right? So I pull out this common factor that now multiplies these things. And now I've got less computations to do. Maybe I can do it in my calculator, especially if I notice I can cancel the 1/2 and the 2. Isn't that nice? So I just got to take 105 pi over 180 times parentheses. Again, so you do the order of operations right. It will do the multiplication before the subtraction unless you enforce what parentheses. So 105 pi over 180 times 19 squared minus 4 squared. Probably I can do that without a calculator. Let's see if I can get this back hopefully. No, they eat other words on these. 105 times second pi to get lots of digits divided by 180 all times parenthesis 19 squared minus 4 squared. Or maybe I know 4 squared is 16. I just enter that directly. That's fine too. Oh, always helps to have your calculator on when you do this. 105. If it looks right. Looks right. 632.24 is what I'm coming out with. Now, where did I say to round this? Round your answer to 3 decimal places, 0.2455. No, this is more accurate than the measurements probably allow, but since I said round here, it's to test your rounding capabilities. I want you to be able to round correctly. And there's more digits. So I'm going to round to the 3 decimal places. That means 3 places past the decimal point. 1, 2, 3. This one is 5 or greater, so I round it up to approximately 632.246. I hope that looks like the answer page of all that work. And I put feet on here. That was an error. It was inches. I don't know why I'm putting feet. Nobody said anything. All right, inches, inches. And the answer should be square inches. Now, maybe that seems like a lot, right? On these things, they suggested after each problem you do a sanity check. Is that realistic? 632? Maybe. Seems a little large to me. So what's the answer saying with that? Find something here. Yeah, I've got something wrong here. What did I do?
I think.
Oh, I know what I did. Yeah, it's off by a factor 2. Did you just figure it out? I put 2 pi radians per 180 degrees. Major mistake, right? It's pi radians for every 180 degrees. 2 pi is 360. Don't do that. That's the Berenstain-Bears lesson, right? Don't do what I do. So it should have been pi, and these 2's don't cancel. So I should have divided that all by a half. There we go. Now we got it. You know, it's a good thing I did a sanity check, right? All right. So this one divided by 2 is 316.1227, etc. Let's try that. 316.1227, etc. And that rounds to 316.123, since after the third digit, the number is 5 or greater. Square inches is my unit because I put inches and squared them, right? An area ought to always be square something or other anyway. All right. Now, does that seem right? That's still a pretty big number. 316 square inches. Here's how you can do your sanity check on what I was doing in my head, not saying anything. This windshield is 105 degrees, a little bigger than 90, right? If I just do a ballpark thing in my head, and you'd be surprised how often this saves you and say, well, this is about 20 inches, and by about 20 inches. It's kind of close to a 20 by 20 square, right? I know what a 20 by 20 square has per square inches. What is it? What's the area of a 20 by 20 square?
400.
Yeah, 400. Yeah, you're giving me the fine. I said 20 squared. I was going to say, yeah. So a square is 20 by 20. The area is 20 squared, or 400. Yeah, that's about right. And that's this is a little less. It's not quite 20 inches, and there's this big area taken out, and only a little area added. That's probably about right. So now I believe my answer. I didn't believe 600 though. All right. I think, oh, it's so close anyway, right? But when that blows up the satellite, then you know, you had to get it right. All right. What else? Anything else that give me trouble? I for sure ask you a triangle problem. You want to see something off of there? Triangles are one of the most important topics of the course, so I have to ask a triangle somewhere. Solve for the unknown sides. We did some of the B problems last time. Let's try some of the A problems this time. Suppose I gave you this one. It's 10 on this side. This is a realistic problem. This is like your garden. 10 feet on this side. And this side we'll call A. And this side we'll call C. And it's a right triangle. And I measure with my protractor or something, 62 degrees over here. How much area do I need to fertilize when I go to buy the fertilizer? How many square feet they're going to ask me, right? Well, you know, I guess I'm not calculating the area, but once you're done, the area is just 1/2 base times height, right? So it's 1/2 10 times A is the area. Here we'll just find the sides, right? What are those sides? You got one? 2 days? What you do is given two pieces of information other than angle. Angle is one piece of information, because once you know one, the other is 90 minus that one. Two pieces of information, you can write a trig relation and either the Pythagorean theorem or the sum of angles is 90 degrees, complementary angles theorem for right triangles, to find everything else. So let's, for the first step, write a trig relation, or a trig equation, relating the two I know and the one I don't know. What could that be?
Sine of 62 equals 10 over C.
Yeah, awesome. Yeah, I noticed this. Sine is opposite over hypotenuse. That's perfect. Yeah, I can put sine of 62 degrees is 10, the opposite side over the hypotenuse, C. Why don't I put cosecant? It also relates those two sides. Yeah, the answer is I can, but the calculator won't do cosecant. I'll have to take 1 over sine to do it anyway. That makes more work. So I'll use the one that's on the calculator when I can. Now, if that's true, now I can, by any algebra technique you like, do this. One way is to say if these two are equal, then their reciprocals are equal, right? C over 10 equals 1 over sine 62 degrees. Don't write cosecant because it's not on the calculator. And this tells me then that C, multiplying both sides by 10, is 10 times the sine of 62 degrees. Right? And Let's compute that in the calculator. Make sure you put your calculator in degrees mode. All right. Do the sanity check, that'll catch it if you don't. Mine's in radian mode, of course. Oops. All right, 10 times 962. And I get about 8.8294, blah, blah, blah. And this problem said, calculate to 4 decimal places, so I better carry a lot of digits.
Shouldn't
Uh-oh.
that be long? It should be 10 times 1 over sign. Shouldn't it?
Oh, yeah, it took 10, I was looking at this. It's 10, yeah, thank you. Yeah, I would have gotten the wrong answer there. 10 divided by, here, multiplying both sides by 10. 10 divided by sine 62. The worst part is I'm recording this. All right, so 10 divided by sine 62. Thank you. Is 11.32570, blah, blah, blah. How did I know that 8 was wrong? Here's a good question. How does he know that 8 is wrong? Yeah, I'm finding the longest side, the hypotenuse. It has to be longer than both these sides. It has to be more than 10. 11 seems like it might be right. And it says round to 4 decimal places, so I round it right here. All right, but you can leave all the decimal places on your calculator if you want. Now the last thing I need to do is find the last side. You can find that with trigonometry. You can say that the cosine of 62 degrees is A over C, which I now know, and relate 2 sides of an unknown. There's nothing wrong with that. I'll give you full credit. The usual procedure is to say, well, the Pythagorean theorem is slightly easier. I'll just use that, and I'll say A is then, by the Pythagorean theorem solved for A. I won't write the Pythagorean theorem directly. That's the square root of the hypotenuse squared, 11.3257 squared, minus the other side squared. Well, the other side squared is just 100. That's easy, right? So I need to do that calculation. I don't have to actually type all these numbers. Remember, I put second ands on here, and the calculator will do that for me. So I'm going to push square root first, which the square root is over the square key. I have to push second square to get the square root. And then I'll push second ands to get the answer back to lots of decimal places. All right. Actually, I hit some extra keys apparently. Square root. I'll have to type it in. 11. Let's see. 1.3257. 100. Then I get about 5.3171 when I round it off. Your answer might be different in the last digit when you do this. That's okay. If you use the trig functions to calculate this, now if you make an error that's arithmetic error that's technically not okay, it might take a point off. But if you did it by another method and got here, like some people do these in the opposite order, find A first and then find C, and you'll find C is a little different. If you do A first, you know, you might with trig, then you might get a little different number than this too. But I expect to get something off by a digit or two on the last digit. But there's that one. And then you kind of do the sanity check, right? You could say, look, since this is 62 degrees, this has to be 38 degrees. I can find the other angle too, so the two add up to 90. The two acute angles in a right triangle always are complementary. 38 there, this is just the angle mark. And then you do the check. Is the short side A opposite the short angle? And it is. Is the middle side opposite the middle angle? It is. And the long side opposite the large angle? And it is. And then you can look and see if the Pythagorean theorem seems to hold. Is this squared plus this squared equal this squared? It looks like it is without a calculation, right? Looks reasonable. So it's, and then, so you can do that kind of a check just to see if it looks way off. This is on. Okay,
Maybe do 22.
22, okay. Thinking maybe I should do 15 too, since that's the one without the answer. Use identities to rewrite each expression as a single trig function. You like this one, it's not as long. It's scary in the beginning and then the easier ones that will give you some confidence. So try these. Send me emails if you have questions or see me at my WebEx office hours. If you can't make those, sometimes I make other times, you know me. So 22, how do I reduce secant theta times cotangent theta? And the instructions basically are just write as a single trig function. What do I do? There's a big hit on these that sometimes works. If you don't see an immediate identity, try writing these all in terms of sine and cosine. Secant, you recall, is 1 over cosine. Cotangent is cosine over sine. Now I see what to do, right? The cosines cancel. I have 1 over sine, and now I see an identity immediately. That's cosecant. There it is. 22D is pretty similar. Now I have cosecant over secant. About that one. If I don't see what to do immediately, I'll write in terms of sine and cosine. Cosecant is 1 over sine. Secant is 1 over cosine. Now I'm testing your algebra again. If you have quotients of quotients, A over B over C over D, right? You can either take this one and write it upside down and multiply them, or I just like to go top times bottom over middle times middle and do it all in steps. So it's top times bottom is cosine over middle times middle is sine. Each of them times 1, if you like. Top times bottom over middle times middle. The ones go away. Oh, I recognize now that's cotangent by my quotient identity, right? So see why you have to memorize the identities and so you can reduce these at the end. The test will take you too long if you don't memorize some of these important identities. The quotient identities, the reciprocal identities, the Pythagorean identities, the even odd identities. And then I guess that's it. I'm going to do one more thing too. On this test, I'm going to say no cofunction identities. These actually were covered at the end of the section. Maybe you looked at those in your book and said, where are those, right? Because we didn't do them in class. So we'll say no cofunction identities yet. I'm going to do them in just a minute. So not on this exam. They're really easy, but since I just gave it to you today, let's not do them on the test. All right, and then finally, 15 gives us a little geometry review, right? It's not just chapter 5, it's also the geometry review. We use that all, of course. Here's the one with no answer on there. Turn the display. And it says, look at this triangle. I don't know if I've drawn it exactly right. Suppose these two sides are parallel. And we have measure X here, 9 here, 6 here, and 11 here. Find X. Anybody get this one? Sometimes when you solve these triangles, just using similar triangles when they're similar is easier than trigonometry, right? So what I do is I say, these are actually similar triangles. How do I know that? What's the proof? This triangle and this triangle have the same angle in common, right? They have the same angle here. And then this angle must be congruent to this angle because these two lines are parallel, right? Remember, this is a transversal cutting two parallel lines. This is alternate interior angles are equal out of geometry, they call it. So these two angles are equal. Well, what if this one and this one are the same? This one is uniquely determined as 180 minus these two. And similarly, these two make this one 180 minus this one, but these two measures are the same as these two, so that makes these the same also. Or you can say parallel lines cut by this transversal. Either way, these are congruent. These two triangles have the same three angles. They're similar. Once I know that, I can write a relation like this. There's a number of ways you can do this. I could say x is to x plus 9. Not x to x plus 9. 9 is to x plus 9. Sorry. 9 over x plus 9. This one is to this side of the small one is to this side of the large one, as this side of the small one is to this side of the large one. 11 is to 17. So small to big equals small to big. Now I can solve that. I really should have done it the other way, though. If I would have a little thinking ahead really counts. I would have done it the other way. I would have had big to small equals big to small, right? You can also do it that way. So I'll turn them upside down at this point, right? X plus 9 is to 9. Big is to small is big is to small. Corresponding sides. Now I can just multiply both sides by 9. X plus 9 equals 9 times 17 over 11. And subtract 9. X equals 9 times 17 over 11 minus 9. I can run that in a calculator, I suppose. Let's see. 9 times 17 is 90, and 63 is 153 11ths. Remember how to multiply these? You take 9 is 9 over 1 top times top over bottom times bottom. And then minus 9, I need to get 11. So I multiply this one top and bottom by 11 and get 99 11ths. And I had to subtract over the common denominator. You subtract the numerators. This gives me 54. Looks like I get 54 over 11. Well, I should put that one in the answer key. You can try it at home and see if you get that. All right, well, got just enough time to do a little bit of new stuff today, huh? Let's make sure I actually finish the chapter. I was, as a mathematician would say, within epsilon of finishing the chapter. In calculus, you'd like to use epsilon for a really tiny, small number getting smaller and smaller, where that phrase comes from. But I was close to finishing. We just have this one thing to do, so this is not for the test. If you have other questions, I have an office hour in a little bit here today, or you can schedule something else possibly. Not for the test. We want to look at the cofunction identities. I'm going to do a proof for right triangles only. And I'm not going to do it for all angles. You could take any angle, this still works. It'd be hard to guess maybe why I only do it for right triangles. Why would I do it for that? It's going to turn out to be a lot easier. It's easy to do it for triangles. And that way, if you forget it, you can remember it by doing the proof for the triangles, right? If I give you the complicated proof in the unit circle, you say, okay, good, you proved it for all cases. But then when you need it on the test, it's so hard to remember that proof. So I'll give you the easy proof that doesn't work in all cases. And just do this. Suppose I have a triangle. This is what helps me as a professional mathematician, right? Is proofs I can remember, right? So I'm going to say, that's the right triangle. That helps me. Not the way it is. If I have two angles in a right triangle, which we usually call alpha and beta, And I can label the sides B opposite beta and A opposite alpha and C for the hypotenuse. I know, let's say that the sine of alpha is what? It's the opposite over the hypotenuse. It's A over C. Right? And now A over C for beta is the adjacent to beta over the hypotenuse, right? So for beta, that's the cosine. So the sine of alpha is equal to the cosine of beta. That's one of the cofunction identities. Let me write it over here because I'm blocking this for you. I'm sorry. Sine alpha equals A over C plus my final result is cosine beta. Similarly, so I'll put hence. Here's the final result. This is the proof. Look, it's a two-step proof. There's only one step in the middle in writing the identity. If I want to calculate the cosine of alpha, oh, wait a minute, I'm not finished actually. I'm sorry, there's one more step, two steps in the middle. But beta, remember from the complementary angles theorem, is 90 minus alpha. So this is actually equal to the cosine of 90 minus alpha. Now here's the cofunction identity. Is that the sine of alpha is the cosine of 90 minus alpha. You can see now why it's called a cofunction identity. It relates sine and cosine, right? And then similarly, I can say cosine of alpha is, well, cosine of alpha is its adjacent over hypotenuse, is B over C. But B over C is opposite over hypotenuse for beta, so it's sine of beta. But beta is 90 minus alpha, so this is sine of 90 minus alpha. And the cofunction identity then says that the cosine of alpha is the sine of 90 minus alpha. So it goes both ways. The sine and the cosine and sine are both related by this. And similarly, you can do this with all six angles. I don't want to do it for all six, you just fall asleep. But you can do exactly the same thing with tangent and cotangent. Tangent alpha turns out to be cotangent of 90 minus alpha. The cotangent of alpha turns out to be the tangent of 90 minus alpha. And the secant and cosecant are also related in the same way. So it's easy to remember, just use the cofunctions of each other. Secant of alpha is the cosecant of 90 minus alpha. And the cosecant is the secant of 90 minus alpha. That's all six of them. I'll put it down here, etc. So hence the cofunction identities are as follows, these six, and they're easy to remember. These are not used a lot. The others are all more important, but you'll see these again somewhere. You don't want to go to calculus class and say, what's that, right? There's something on here, as I recall. Right at the end, we skipped those. Yeah, at the beginning, I'm sorry. So here's 5.4, number 1. A. Cosine of 34 degrees is the sine of what angle? Very easy, right? Just put 90 minus 34 degrees by the cofunction identity. 56. And here's the second part. This also works in radians. So this is also known as, AKA, cosine, sine alpha equals cosine pi over 2 minus alpha if you write it in radians. Right? Replace 90 degrees with pi over 2. And again, the others, pi over 2 minus instead of 90 minus. So let's do this next one. Now I'll do 5.4, 1b. Maybe you want this on the test. They're not very hard. You just want to see these. I told you these aren't some of the most important. Cosine of pi over 3 is the sine of what? Yeah. I don't want to put them on the last day. Somebody's out today or something. We were frustrated when I already told them. Anyway, so, yeah, they're not bad, are they? All you have to do is take pi over 2 minus the other angle, right? Pi over 2 minus pi over 3. Now, here's the trick on the radians. Fractions are harder, right? So what do you do to get to subtract fractions? Common denominator, multiply this one top and bottom by that denominator, 3 and 3, so you get 3 pi over 6. Multiply this one top and bottom by the other denominator, you got 2 pi over 6. 3 pi minus 2 pi is pi, all over 6. So the answer here is pi over 6. There's my calculation. All right. That's all there is to the cofunction identities. We'll use those seldom. All right. Good riddance to that then. Try some of those applied problems if you haven't too. We didn't do it. Maybe we should do one more applied problem. I hate to eat up a whole hour of that. With review, but maybe that's what's best. I don't know. Just remember, we didn't ever get to this one. I'm going to do one more review problem. So this one is review for the test. I just realized I need to do one of the diagrams. Here's number 18 off the practice exam. There's also a bunch of review problems, or geometry problems in the homework at the end of the last section there, 5.4. Here's somebody with their, looks like a sextant in hand or something. And they're trying to measure height of a building. And they're holding this measuring device 5 feet up, right at their eye level or something. And suppose it goes up the building, or a street lamp here, and measures that the angle up from eye level is alpha, and it also measures an angle down to the bottom of the lamp. And you can break this up when you do these geometry, these word problems. Always draw the picture. This one I gave you the picture, but I may not have. Suppose I call this height D and this height H. D for distance, H for height or something, or height and depth. And then X will be the distance you are from the lamp post. Suppose I tell you the eye level is D equals 5. Above the horizontal ground, that you're standing X equals 20 feet from the lamp post, and the angle alpha is 37 degrees. Find the height of the lamp post. What about that?
Professor,
Yeah.
that's actually number 19.
Oh, I'm sorry. Yeah, you know what? I brought an old copy of the test. You're right. I'm supposed to look at it on here. I had adjusted the practice model. Yeah, you're right. That's actually my. I changed the problems a little. There it is, 19 on there. I put it on the display here. So how do I find that? The ground is horizontal, so these are both 5. This is a right angle, and this is a right angle. I have 2 right triangles, right? This is an applied problem. It's tricky because you have 2 right triangles, right? Just like you had 2 sectors in the other problem. This is what you do in real life, right? So if I just find D and H by right triangles, then I can add them to get the height of the lamppost that I want. I already used H, so I'll just call that height. Well, let's see. I'm given that if I write these in, this is 37 degrees, and this distance, X, is 20 feet, so I know 2 pieces of information in this triangle. That means I can solve the triangle, find everything. I don't need everything. I don't need this angle. I don't need the hypotenuse. I only need H. So I can, from this triangle, compute, I can relate h, what I want, to the two numbers I know, saying sine of 37 degrees is the opposite side, h, over the, oops, not sine, it's tangent, isn't it? Opposite over the adjacent is h over 20. There we go. The tangent of 37 degrees is h over 20. I also know over here, d is 5 already, just from the rectangle. So I'll say h now, if I multiply both sides by 20, is 20 times tangent of 37 degrees. Tangent is on my calculator, so I'm in luck. I just have to put it in degrees mode. And I get h equals 15.07 blah, 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 feet. And so the height that I want is 5 feet more than that. 5 plus 15 point, so let's say this is approximately 15 feet. 5 plus 15 is 20 feet. All right. So maybe you get something like that on the test. Maybe you'll have to actually calculate the bottom triangle. If I instead of telling you this is 5 feet, maybe tell you the angle on this side or something. If I say angle of inclination, what angle is that? Remember we did the 5 problem last time? That's the angle up from horizontal. The angle of declination is the angle down. So maybe on the test, I'll give you angle of inclination, angle of declination, say you're 20 feet away. What's the height? Then you have to solve both triangles. That'd be a good problem. Think about that. Giving you some ideas. All right. So there's that. We can maybe charge ahead just a little bit today. So feel better. Let's do the last second problem here. The next thing is to look at graphs of sine and cosine. And I want to just motivate these a little bit. Well, this will just get us started for next week. So once again, not for this exam. Suppose I consider the unit circle again. I told you it's a very important part of the course. And now I think of letting the angle theta run around counterclockwise, like so. And I look at the point on the end where it intersects the circle, and I remember that we defined that to be cosine theta sine theta, the coordinates of that. I wonder if I can sketch a graph over here with theta on this axis versus sine theta on this axis. So I'm going to plot y equals sine theta. Well, it's theta versus y, if you like. And it'll be the graph of y equals sine theta. Well, this is kind of cool because look what you can do. And if you look up Wikipedia, Google Wikipedia graph of sine and cosine, it will show you a moving picture. This is beautiful. I'll probably put it up next time. But when you put the angle a little, sine is the y coordinate, right? So it looks like this tall. So theta goes out a little. So when theta is 0 first, for 0 degrees, you go to the point 1, 0, right? So sine is the y coordinate, it's 0. So you make a chart over here. You say, here's theta versus sine theta on the unit circle. If theta is 0, I go out here, angle 0. And the sine is the y coordinate, it's 0. So I plot the point 0, 0. Then the angle goes up a little, and y goes up a little. So I've got something like that. The next angle I have memorized is 30 degrees. So I go up 30 degrees, and I remember that that's a 1/2 square root of 3 over 2, one triangle. So y is a half, and x is square root of 3 over 2. This point right here, you can look at that diagram I showed you in the unit circle. It has all these marked already. X is square root of 3 over 2. Y is a half. So at theta equals 30 degrees. Actually, instead of 30 degrees, let me call it pi over 6, the radians version. And say at pi over 6, I've actually gone up to a half. So I can plot that point. Now I go up to a steeper angle. Maybe here is 45 degrees. And I take the point, and remember on this triangle, it's square root 2 over 2, square root 2 over 2. And so the cosine and the sine are both square root 2 over 2. And I can add that to my chart here. So here's that pi over 6. I get 1/2. But at pi over 4, 45 degrees, I get square root 2 over 2. Then at 60 degrees, that's the next one I memorized. Here's 60 degrees. I get the point with these. Right now, this side is 1/2, and this side is square root 3 over 2. So 1/2 square root 3 over 2. I observe the sine is now square root 3 over 2. And angle pi over 3 in radians, 60 degrees. And then up here, if I go to 90 degrees, the point is 0, 1, so the sine is equal to 1. The angle is pi over 2 for 90 degrees. So I can plot all these points, pi over 6, pi over 4, pi over 3, pi over 2, and make a graph of theta versus sine theta. It looks kind of like this. And this is y equals 1 here. This is square root 3 over 2 here. This one's at square root 2 over 2. Maybe you can see that, I hope online. And this one's 1/2. And it makes a curve, if I draw it correctly, that looks something like this. And then I can keep going. An interesting thing happens. As I get larger angles, maybe I go around here to 2 pi over 3. The sine goes back to square root 3 over 2. So I get the point 1/2 square root 3 over 2. The same y coordinate at pi over 3, at 2 pi over 3, that I got at pi over 3. And similarly, at 3 pi over 4, where this is a 45-degree angle left, once again, I get square root 2 over 2, square root 2 over 2, and the sine is square root 2 over 2. The angle in standard position, 3 pi over 4. So I'm getting the same numbers descending. Over here at 5 pi over 6, 30 degrees left, I'm going to wind up with 1/2 again. And an angle pi, 180 degrees, I'm going to get the point minus 1, 0. The sine is going to be 0 again. So now I can draw these same points descending here, 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 and here at pi reaching 0. And I get a curve that has sort of a symmetry like that. What happens if I keep going around these angles? Yeah, it's going to go all the way around the circle, and the y coordinates are going to be the same but negative, right? Over here, instead of, let me draw this one in, it was minus square root 3 over 2, 1/2. The y coordinate is going to be negative. At this one, I'm going to get minus square root 3 over 2, minus 1/2. So as I keep going, all the y coordinates will be the same. And then here, minus square root 2 over 2. I should have called this minus x coordinates. These are all negative. Put the side lengths. I should put the coordinates here. Minus square root 2 over 2, minus square root 2 over 2. And then this one at 60 degrees past a straight angle, I'll put minus 1/2 minus square root 3 over 2. And the point is, I start getting exactly the same values for y, but negative. And so what's going to happen is I'm going to go around like this with another one of these things, but upside down. The same y coordinate is negative. And I do that in pi more radians, so I finish up here with 2 pi. You can go ahead and plot those, and like I said, on Wikipedia, they got the nice revolving picture, and you can watch the line going to go up here, like this goes just like that. It's really beautiful. And then what happens after you complete a circle, you can keep going with the angle, and it repeats all those things all over again. What you find out is that this just goes over and over forever. Right? It's the song that never ends. I sing. It just goes over and over and over as the angle goes around and around and around. And this is the graph of y equals sine theta. Turns out the cosine is very similar. Cosine, however, is the x-coordinate, so it starts at 1. Then it goes to square root 3 over 2. Then square root 2 over 2 1/2. It does exactly the same numbers, just starting at 1. And so it starts up here at 1. This is 1. And the curve, you notice, goes between plus and minus 1, by the way. The highest coordinate you got was 1, and the lowest was, oops, I wrote pi 0, this should have been pi minus 1. Well, I'm fixing all my mistakes just in time, huh? Pi minus 1, y coordinate is minus 1. Down here. No, this was 0, this is right, okay. Minus 1, I didn't do it. That's when you get down to 3 pi over 2. You get minus 1. But it goes down to minus 1 of 3 pi over 2 here. And the cosine does the same thing. It just starts at 1, so it goes like this. It crosses here where this one's at the top. It bottoms out where this one crosses. So one crosses and one peaks or valleys at the same time, and you get a curve that looks like that. And this, we'll say, is the graph of y equals cosine theta, and we'll do those some more next time. No new problems, just study for the test, all right? Thank you for your time.